Our project is trajectory optimization for quadruped traversing a rotating platform. I'm Ethan Yang.
And I'm Kenneth Moon.
Our motivation for this project came from the ladder climb game in Carnivals. In this game, one has to climb up a deceptively unstable ladder to touch a button. The catch is that the ladder is attached only at one point on each end, so it freely rotates and the support is similar to climbing over a tightrope. Our simplification of the ladder climb game turns the ladder into a solid, rotating platform. Like the ladder, the platform is free to rotate, so walking across requires awareness of one's center of mass. We modeled the quadruped as Little Dog and based our optimization off of the gait optimization from the under-actuated repository.
Our general approach to this problem was to use direct transcription. We initially used the pre-specified contact mode sequence to find the trajectory for walking across the platform. In the order shown on the slide, our variables were the time step, generalized positions, generalized velocities, contact forces between the robot and the platform, the center of mass and its time derivatives, the angular momentum of the robot about its center of mass and its time derivative, and the angular acceleration of the rotating platform. These were sufficient to encode the physical constraints of our system, as we will see in the next slides. One important set of constraints was the periodicity constraints. Since we initially aimed to find the periodic gait across the platform, we had to ensure that the leg positions at the end matched the ones at the beginning, and mirrored in the case of walking. We also had to ensure that the platform angle and angular velocity were mirrored by the end of the stride, as you can see in these constraints. We also implemented contact constraints to emulate static friction. The constraints on the slide show our approximation of a friction cone, which constrains each component of friction in the plane of contact. We then used the pre-specified mode sequence to ensure that the normal force was 0 on time steps where the feet should not be touching the platform.
We solved our trajectory optimization with SNOPT. We ran our optimization for progressively harder and harder states. We started by specifying the rotational inertia of the platform to be extremely high to model physical ground, and progressively lowered it as we were more confident that our optimization was correct. We were also able to optimize for slightly off-center initial angles for the bridge, but it required incrementing the angle by incredibly small amounts and passing in the solution from the previous angle. Trying to directly solve for the final angles fails. Here's the successful optimization with an initial platform angle of 0 radians. Here's the result with an initial angle of 0.01 radians. Despite the tiny change in angle, the behavior is completely different. The difference in the two trajectories is apparent when graphing the deviation of the center of mass from the center line and the angle the platform takes over time. Notice that for the 0.01 initial angle, the center of mass position must take a more aggressive line to stabilize. The pre-specified mode sequence has limitations in only being able to solve for a limited space of initial conditions. In particular, we weren't able to find solutions for when Little Dog started off-center and when the angle magnitude was too large. Different initial conditions require more aggressive and different mode sequences, which are too hard to plan a priori. We use complementarity constraints to allow the optimizer to plan the mode sequence implicitly. Let P be the position of a given foot with respect to the bridge, where the second, or Z component, is orthogonal to the bridge. The first complementarity constraint enforces that the magnitude of the respective contact force is 0 when the foot is not touching the ground. The second and third enforce that the feet do not slip when the contact force is non-zero. We assume non-slip for simplicity in our model.
When we attempted to implement the complementarity constraints, we found it unexpectedly difficult to get the optimizer to report a feasible solution, or even an infeasible solution remotely similar to what we would expect. Based on some infeasible approximations produced by SNOPT, it appears that the optimizer tended to get stuck in local optima. For instance, on multiple occasions, the optimizer started the robot far above the bridge and seemed to try to throw the robot into the goal position. When we constrained the height, the infeasible solution that would then return would just have the robot floating over the bridge. Ultimately, we were unable to have the complementarity constraints produce a feasible trajectory. In the end, there are many possible paths towards getting closer to our goal. First of all, we could try reformulating our complementarity constraints so that the solver does not get stuck, as we saw on the previous slide. We could also add a more realistic friction model which includes both static and kinetic friction, which may allow more trajectories to be explored. Ultimately, to make a controller for the robot crossing the bridge, we would need stabilization in the form of time-varying LQR over our found trajectories.